Hello everyone! Welcome to the introductory video for the exact and inexact ordinary differential equations. Although the simple first order dE y dx plus x dy is equals to 0 is both separable and linear, we can solve the equation in an alternative manner by recognizing that the expression on the left-hand side of the equality is the differential function f of xy is equals to xy. That is, the derivative of xy is equals to y dx plus x dy. In this section, we examine first-order equation written in differential form m of xy dx plus n of xy dy is equals to 0. Such equation can either fall and be solved under the exact or inexact using integrating factor. But before that, we have to remember one topic from differential calculus, the partial derivatives. A partial derivative of a function of several variables is its derivative with respect to one of those variables, with others held constant. For example, let f of xy is equals to y cubed x squared. Calculate the partial derivative of x with respect to x. To calculate the partial derivative of f with respect to x, we simply view y as being a fixed number and calculate the ordinary derivative with respect to x. The first time you do this, it might be easiest to set y is equals to b, where b is constant, to remind you that you should treat y as though it were a number rather than a variable. Then the partial derivative is the same as the ordinary derivative of a function. G of x is equals to b cubed x squared. The partial derivative of g with respect to x is equals to 2b cubed of x. Now, we remember that b is equals to y and substitute y back in to conclude that the partial derivative of x with respect of f with respect to x of xy is equals to 2y cubed of x.
This review on partial derivatives gives us the very core for the test for exactness of differential equations in the form we had above. Going back to our first order dE form, m of x of y dx plus n of x of y dy equals 0. Let m and n be continuous and have continuous first partial derivatives as the partial derivative of m with respect to y and partial derivative of n with respect to x. If these two are equal, the differential equation is considered as exact dE. An expression is called as an exact dE if there exists a function of f, xy of two real variables such that the expression equals the total differential equation. Now let us solve the given differential equation. Quantity 2x plus 4y minus 1 dx plus quantity 4x plus 6y plus 1 dy equals 0. We check this equation for exactness. So the partial of m with respect to y is equivalent to partial of 2x plus 4y minus 1 with respect to y. Let 2x equals b, which is a constant. Partial of m with respect to y is equivalent to partial of b plus 4y minus 1 with respect to y. Therefore, the partial of m with respect to y is equivalent to 4. We know that the derivative of a constant is 0. Therefore, we are only left with the derivative of 4y, which is 4. Then, the partial of m with respect to x is equivalent to the partial of 4x plus 6y plus 1 with respect to x. So let us let 6y equals b, which is a constant. The partial of m with respect to x is equal to the partial of 4x plus b minus 1 with respect to x, giving us the partial of m with respect to s equals 4. Therefore, the dE is exact. And now, what we'll do is then take the antiderivatives with respect to the appropriate variables. So we will antiderivative m in terms of x and n in terms of y respectively. So the integral of m dx is equivalent to the integral of 2x plus 4y minus 1 dx, giving us the integral of 2x dx plus the integral of 4y dx minus the integral of dx. Let us move the constant outside the integral signs and let us integrate. It is equal to 2 quantity x squared over 2 plus 4xy minus x plus c 1. The antiderivative of n with respect to y is equivalent to the integral of 4x plus 6y plus 1 dy is equivalent to the integral of 4x dy plus the integral of 6y dy plus integral of dy, giving us 4xy plus 3y squared plus y plus c2x. And our constant of integration is a function involving the other variable x. So what we're saying so far is that our function contains these terms plus also possibly some other terms that involve y. Our function also includes these terms, possibly some other terms involving x. So if we combine all of these ideas into one potential function here at the end, make sure we'll include x squared. Also, we'll want to include 4xy, which will take care of those in the two equations. Then include 3y squared over there and the minus x and plus y. So we all have all our terms there, and on the other side, we could just have some constant. And that's it. This is our function with the original properties that we started with. X squared plus 4xy plus 3y squared minus x plus y equals c.
So let's move on to the next example. Try to pause this video for a moment and answer this one as a practice. So we have 2xy minus sine x dx plus x squared minus cosine y dy is equals to 0. This differential equation is exact because partial derivative of m with respect to x is equals to partial derivative of x squared minus cosine y with respect to x is equals to 2x. Partial derivative of n with respect to y is equals to partial derivative of 2xy minus sine x with respect to y is equals to 2x. We find the function u of x of y from the system of two equations. Partial derivative of u with respect to x is equals to 2xy minus sine x, and partial derivative of u with respect to y is equals to x squared minus cosine y. By integrating the first equation with respect to the variable x, we have u, function of xy, integrate 2xy minus sine x dx is equals to x squared plus y plus cosine x plus phi of y. Plugging in the second equation, we obtain derivative of u with respect to y, partial derivative of u of x squared y plus cosine y plus phi of y is equals to x squared minus cosine y. So, x squared plus derivative of phi of y is equals to x squared minus cosine y. Therefore, partial of phi of y is equals to negative cosine y. Hence, phi of y is equals to integral of negative cosine y dy is equals to sine dy. Thus, the function of u xy is function of u xy is equals to x squared y plus cosine y minus sine y. So, that the formula solution of the differential equation is given by the implicit formula x squared y plus cosine y minus sine y is equals to c. Did you get the same answer? If no, try to review again the lesson and practice more. However, if you got it right, continue this video and let's move on to the inexact differential equation made exact using an integrating factor.
For the inexact differential equation, going back to our first order DE form, m of xy dx plus n of xy dy is equal to 0 that have continuous first partial derivatives as partial derivative of m with respect to y and partial derivative of n with respect to x. If these two are not equal, the differential equation is considered as an exact DE. For us to solve the equation, we need to transform it into an exact differential equation. In order to do that, we need to find an integrating factor to multiply the equation by. But before doing so, we have to familiarize ourselves with these formulas. The integrating factor is the factor of which if we are going to multiply the whole non-exact DE, where upon doing so then, we will be making the DE exact. As we go on our discussion, let us try to solve this one. Quantity y minus xy dx plus x dy is equal to 0. First, we have to test for exactness. So the partial derivative of m with respect to y is equal to derivative of y minus xy over dy. Let x is equal to b. So the partial derivative of m with respect to y is equal to the derivative of y minus by with respect to y. So we get 1 minus x. The derivative of y is 1 and the derivative of b with respect to y is negative 1. Therefore, substituting x to b gives us 1 minus x. Then, the partial derivative of n with respect to x is equal to dx with respect to x. So we get 1. Therefore, the partial derivative of m with respect to y is not equal to the partial derivative of n with respect to x. Thus, the equation is inexact. Now we will be using the formula given above to get the integrating factor. So let's try this, the first formula. So 1 over n times the partial derivative of n with respect to y subtracted by the partial derivative of n with respect to x is equal to f of x. 1 over x times, since our partial derivative of n with respect to y is 1 minus x, then we will subtract it with partial derivative of n with respect to dx as 1. We cancel the 1's. We will remain with 1 over x times the negative x. That will be our function of x. So we multiply it and we get negative x over x or negative 1. As you can see, the answer we got from the formula is a term involving only a variable x. However, if we use the second formula, 1 over m times the partial derivative of n with respect to y minus the partial derivative of n with respect to x, we get 1 over 1 minus xy times negative x. And then, we will remain with f of y is equal to negative x over y minus xy. We will not use that. As you can see, we had an answer with two variables in it. So we must not use the second formula, but rather the answer we got from the first formula, which is negative 1. Using the first formula in getting the if is equal to e integral of f of x dx will be used, we simply substitute if is equal to e raised to the integral of negative 1 dx. So we will put the negative sign in front of the integral and we will get e raised to negative x. Now we have the integrating factor, which is e raised to negative x, which we will multiply with the original equation in order to transform it from inexact to exact. So the y minus xy dx plus x dy is equal to 0. Multiplied by the integrating factor e raised to negative x, we get y minus xy e raised to negative x dx plus x e raised to negative x dy is equal to 0. So we will distribute the e raised to negative x to y minus xy and we get y e raised to negative x minus xy e raised to negative x, that will be our m dx plus x e raised to negative x, and that will be our n dy. Now that we have our new equation, let us check for exactness. So we get the partial derivative of n with respect to y e raised to negative x minus xy e raised to negative x, we get e raised to negative x minus x e raised to negative x. In the partial derivative of n with respect to x, we get e raised to negative x minus x e raised to negative x. Therefore, the differential equation is the exact. And now, that what we'll do is follow the step we had with the exact differential equation.
The next step is to take the antiderivatives with respect to the appropriate variables. So we will antiderivative m in terms of x and n in terms of y respectively. The partial derivative of f with respect to x is equals to m, x, and y. The partial derivative of f with respect to x is equal to y e raised to negative x minus x y e raised to negative x. Then we integrate this equation. Integration of y e raised to negative x minus x y e raised to negative x dx. We use the formula of IBP, or the integration by parts. The formula for the integration by parts is uv minus integral of b du. First, we let u is equals to x. Du is equals to dx. dv is equals to e raised to negative x dx. v is equals to negative e raised to negative x. So, the value of f now is equal to y integral of e raised to negative x dx minus y integral of x e raised to negative x dx. Next, this equation will be solved by next step. Negative y e raised to negative x minus y, the quantity of minus x e raised to negative x minus integral of negative e raised to negative x dx. So, we integrate the next term. Minus y e raised to negative x minus y bracket minus x e raised to negative x plus the integral of e raised to negative x dx. Then negative y e raised to negative x minus y open bracket minus x e raised to negative x minus e raised to negative x. Then we cancel the term minus y e raised to negative x and y e raised to negative x. Then the remain terms are x y e raised to negative x plus q of y. The next is the partial derivative of f with respect to y is equals to n, x and y. Then we get the integral of that partial derivative, the integral of x e raised to negative x dy. F now is equals to x e raised to negative x integral of dy. F is equals to x e raised to negative x y plus r of x. So if we combine all of these ideas into one potential function, here at the end, make sure we'll include x, y, e raised to negative x, which will take care of those in the two equations. Then there's no other more terms. And that's it. This is our function with the original properties that we started with y minus xy dx plus x dy is equals to 0. So the final answer is x, y, e raised to negative x equals to c. That sums up our day. Thank you for watching, and do not forget to practice solving this kind of problems. So click the notification bell, then goodbye. This is our video.